Hello, calculus students. Here we are with a review of complex numbers. Remember I, it's the square root of negative 1. That means I squared is negative 1. I squared equals negative 1. And the complex numbers can be written in combination with I, like 3 plus 2I. We have both a real part and an imaginary part. Now, two complex numbers are equal if their real parts are equal and their imaginary parts are equal. So let's imagine this problem here. Find x and y if x minus 3yi equals y plus 6i. So we can set the real parts equal to each other. That is, x equals y. And the imaginary parts equal to each other. That is, negative 3yi equals 6i. Or if you divide through by I, negative 3y equals 6. So y equals negative 2. Now you can put this negative 2 in over here to get x equals negative 2 as well. So there's your answer for both x and y. Now, and subtracting complex numbers is a lot like what we do with polynomials. 3 plus 2i minus 9 plus 8i. And now we put the real parts together and the imaginary parts together to come up with negative 6 plus 10i. Multiply is a little trickier. It involves, here the book has gone through a lengthy diagram on the process. And you don't have to memorize this as a formula. You know FOIL perfectly well here. FOIL would be first, which would be 27. Outer, negative 24i. Inner, which would be these two, 18i. Plus last, which would be negative 16i squared. Now, some get stopped by just combining these two. But I squared is negative 1. So it's negative 16 times negative 1. And so we have 27 plus negative 6i plus 16, giving us a total of 43 minus 6i. Complex conjugates are going to be handy for doing division. And we're going to see that when we solve quadratic formulas with real coefficients, quadratic equations, that the answers come in conjugate pairs like this, if they do have complex answers. Now, you don't have to go through FOIL on this one. You can go ahead and just square each of these parts and just call it 5 squared plus 2 squared. 25 and 4 is 29. You don't have to go through all this reproof. So note the contrast though. If it's just a plus b times a minus b, that's a squared minus b squared. But complex conjugates a plus bi times a minus bi, because the I squared in there changes to a squared plus b squared. So note the difference when to use each one of these. It's going to come up here when we're doing dividing. To divide complex numbers, you multiply both the numerator and the denominator by the conjugate of the denominator. So we take the 3 plus 2i and multiply by 3 minus 2i. To make an equivalent fraction, you have to multiply both numerator and denominator by the same thing. So there we go. Now I can FOIL out the top. First is 18. Outer is minus 12i. Inner is minus 9i. And last is plus 6i squared. All over. Now on the bottom we have 3 squared plus 2 squared. So the top works out to be 18 minus 21i plus negative 6 over 9 and 4. Or 18 minus 6 is 12 minus 21i over 13. And then if it's a complex number, we're going to separate out this part. There's the real part, 12 thirteenths plus negative 21 thirteenths times I. Square roots of negative numbers now. This comes up a lot when we solve with quadratic formula. square root of negative 45, we have to look for the perfect squares inside here. Well, the first thing we do is write as the square root of 45 times I. And then you can get a perfect square. That's square root of 9 times square root of 5I. So 3 square root of 5I. And sometimes it's written this way, 3I square root of 5, just so people don't mistakenly think the I is in the square root. Finally, adding up two fractions. So, kind of torn here, do we rationalize this first and get rid of the I in the denominator, or do we add the two fractions? Well, in this case, you do both in the same step, because you have a least common denominator of 1 plus I times 1 minus I, which works out to be 1 squared plus 1 squared, or 2. So that's your LCD. You can use the LCD in the fact of adding up the two fractions. So 2 over 1 plus I minus 3 over 1 minus I. And we're going to multiply both numerator and denominator here, in this case, by 1 minus I over 1 minus I. And in this fraction by 1 plus I over 1 plus I. So you get 2 minus 2I minus 3 plus 3I in quantities all over the LCD. So the 2 plus negative 2I plus negative 3 plus negative 3I over the LCD, which we found out was just 2. So that's negative 1 plus negative 5I over 2. Negative a half plus negative 5 halves I for the division problem. Okay, flange out.